What the Schmidt? Examples is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found at the webpage link in the description. This video, What the Schmidt? Examples, gives examples of three related concepts: dimensionless number or dimensionless group, dimensional homogeneity, and the argument to any transcendental function has to be dimensionless. As mentioned in Where Does Sherwood Hide His Unit? Principles, the most famous dimensionless number is the Reynolds number, given as the fluid density times the fluid velocity times a characteristic length, such as the diameter of a pipe, and divided by the dynamic viscosity, mu. Or the fluid velocity times the characteristic length divided by the kinematic viscosity, nu. The Reynolds number is a measure of the relative importance of a momentum, given by the velocity times the density, to the viscous forces given by the ratio of the viscosity to the diameter. So at low Reynolds numbers, the resistance to flow is governed by the viscous drag, and at high Reynolds numbers, the resistance to flow is governed by inertial forces. We discuss in later videos what low and high mean, but for pipe flow, the transition from one to another is usually around 2,000 to 3,000. There are lots and lots of dimensionless numbers. For us, the important thing is that they are all dimensionless, so as long as you are consistent in your set of units, everything should cancel, and the value should come out as a pure number. Let's do one actual numerical example in both SI and American engineering units for the Reynolds number. Suppose you have water flowing in a 3-inch or 76.3 millimeter pipe at a velocity of 10 feet per second, or 3.048 meters per second. The density of the fluid is 62.4 pounds mass per cubic foot, or 999.55 kilograms per cubic meter. The viscosity of water is 2.5791 times 10 to the minus 5 pounds per second per square foot, or 1.2349 times 10 to the minus 3 newtons second per square meter. We have to convert the inches to feet and the millimeters to meters. Then, in American engineering units, rho VD over mu equals 6.049 times 10 to the 6th pound mass foot per pound force second squared. I thought it was supposed to be unitless. Back in the furlongs per fortnight video, we learned that 1 is equal to 1 pound force second squared over 32.174 pound mass foot. If we multiply our result by 1 in the form of 1 pound per second squared over 32.174 pound mass foot, we get a 1.880 times 10 to the 5th, and it's unitless, as a dimensionless number should be. In SI, rho VD over mu equals 999.55 kilogram per cubic meter times 3.048 meters per second times 0.0762 meters over 1.2349 times 10 to the minus 3 newton seconds per square meter, resulting in 1.880 times 10 to the 5th kilogram meter per newton second squared. In SI, 1 is equal to 1 newton second squared per kilogram meter. So multiplying by 1 newton second squared per kilogram meter gives 1.880 times 10 to the 5th, and it's unitless, as a dimensionless number should be. The answer is the same in American engineering, or SI, as it should be. Since the value is greater than 3,000, the flow is in the inertial regime, or turbulent regime. Almost all dimensionless numbers express the relative importance of two different engineering quantities. Dimensionless numbers find extensive use in chemical engineering. There are lists of dimensionless numbers, and if you want a fairly comprehensive one, you can search Wikipedia or follow the link in the description for it. Here is a very small list of dimensionless numbers that are important in chemical engineering. The definitions for the variables are on the website linked in the description. First, the Nusselt number. The Nusselt number is equal to the heat transfer coefficient times the characteristic length divided by the thermal conductivity. It is a measure of the ratio of convective to conductive heat transfer, or in other words, the relative importance of convection to conduction in heat transfer. Next is the Prandtl number, which is given as the ratio of the kinematic viscosity to the thermal diffusivity, or the heat capacity times the dynamic viscosity divided by the thermal conductivity. It is a measure of the ratio of viscous diffusion to thermal diffusion. Next is the Fourier number, and it is given as thermal diffusivity times the time divided by the characteristic length squared. It is the ratio of the thermal diffusive rate to the storage rate in transient heat transfer. Next is the Sherwood number, but Professor Sherwood always referred to it as the mass transfer Nusselt number, and you might see the similarity. The Sherwood number is the mass transfer coefficient times the characteristic length divided by the mass diffusivity. The Sherwood number is basically the ratio of the importance of convective transport to diffusive mass transport. Finally is the Schmidt number, which is the analog of the Prandtl number, but for mass transfer. is the kinematic viscosity divided by the mass diffusivity of the liquid, or the dynamic viscosity divided by the density and the diffusivity of the fluid. So if you divide your dynamic viscosity by your density and your diffusivity, you've got your Schmidt together. This is the ratio of the importance of viscous diffusion to mass diffusion. As I said, there are lots and lots of dimensionless numbers. For us, the important thing is that they are all dimensionless. So as long as you are consistent in your set of units, everything should cancel, and the value should come out as a pure number. Again, for a much longer list, search Wikipedia and dimensionless numbers in fluid mechanics. Our first example is the integrated form of the rocket equation without drag or gravity. The change in velocity is the specific impulse times the standard gravity times the natural log of the launch mass divided by the dry mass. As mentioned, transcendental functions such as the natural log are dimensionless and must have dimensionless arguments. So m0 and mf must have the same units, and ISP times g0 must have the same dimensions as delta v. For SI units, delta v has units of meters per second, and g0 has units of meters per second squared. So ISP, the specific impulse, must have units of seconds. As a double check, the specific impulse is the impulse generated by the consumption of fuel in Newton seconds divided by the weight of fuel in newtons, giving units of seconds. Our second example is the non-integrated form of the rocket equation, with both drag and gravity for vertical ascent from Earth's surface. The rocket acceleration is equal to the thrust over the rocket mass minus g minus 1/2 the drag coefficient times the projected area times the air density divided by the rocket mass times the vertical velocity squared. In SI, the acceleration is in meters per second squared, so the three other terms must have the same units. Mass is in kilograms, so the thrust must be in kilograms meters per second squared, or in newtons, which it is. G is in meters per second squared. For the final term, rho over m is per meter cubed. Area is in meters squared, velocity squared is in meters squared per second squared, so the drag coefficient must be dimensionless, which it is. For the curious, the drag coefficient is a function of the Reynolds number, which is also dimensionless. Dimensional homogeneity makes it easier to figure out the units of a constant or parameter in an equation, because you know that all of the terms in an equation must have the same units. Finally, arguments of transcendental functions. The arguments of transcendental functions such as the sine, the cosine, the exponential, the log, and others must be a pure number. Let's do an example that will give us a lot of practice. For a rocket that is flying vertically in the Earth's atmosphere with a constant thrust and a constant drag coefficient, the altitude is given by the altitude minus the initial altitude is equal to the maximum velocity squared over b times the natural log of the hyperbolic cosine of b over vmax time t minus t0 plus the inverse hyperbolic tangent of the initial velocity over vmax minus the natural log of the hyperbolic cosine of the inverse hyperbolic tangent of v0 over vmax. Starting at the end, v0 over vmax is dimensionless, and it must be. And the inverse hyperbolic tangent is dimensionless as it must be for the hyperbolic cosine, which is dimensionless as it must be for the natural log, which is also dimensionless. We've already done the inverse hyperbolic tangent of v0 over vmax, so moving on, b over vmax times t minus t0 must be dimensionless. Vmax has SI units of meters per second, and t0 have dimensions of seconds, so b must have dimensions of meters per second squared, or acceleration, which means that vmax squared over b must be meters squared per second squared over meters per second squared, or meters, which matches with our x and x0. The takeaways for this video are the same as the first three takeaways for the previous video. 1. There are ways to combine variables or measured quantities to create dimensionless numbers, which help reduce the measurements you need to make to characterize your system. 2. All of the terms in an equation must have the same dimensions. In other words, equations must have dimensional homogeneity. 3. Arguments of transcendental functions must be dimensionless. Thanks for watching. This video was brought to you by the DOFPro team.